and it will cancel out or not be included in the reaction. So there are several types of single displacement reactions. You can have a metal plus an acid make hydrogen and salt. And so this would be something like magnesium plus hydrochloric acid making hydrogen gas, and the salt here would be the magnesium and the chloride, MgCl2, and you would need to balance that reaction. And by the way, if you go to the website and open this PowerPoint, there these yellow titles have active links, or at least at one time they were active links at 2 videos that show this kind of reaction. So if you have an active metal, now by active metal here we're talking things like the alkali metals or the alkaline earth metals that are in the lower part of their column. So things like magnesium and calcium. Let's see, got to get my periodic table in front of me. Amazing how long that takes when you're just sitting there watching the video for me to find my periodic table. There we go. I thought I had a periodic table. I just keep pushing the wrong button. So yes, magnesium, calcium more so reactive, and strontium even more reactive. So those would be the active metals, the alkali metals, and those lower alkaline earth metals. When they react with water, we get hydrogen and a metal hydroxide. So here we're reacting with an acid, here we're reacting with water, and we get a very similar reaction. That would be things like calcium plus water make the hydrogen gas and the metal calcium hydroxide. An example of that kind of single displacement reaction. If you have a metal and a salt, you may get a metal and a salt. So this might be something like iron and aqueous copper sulfate, and this is going to occur in solution, and we would get copper and iron sulfate. And this is also an aqueous solution. So the sulfate ends up being a spectator ion, and we just have 2 plus here, 2 plus here. Don't know if, let's just make sure we get that. Iron plus Cu2 plus produces Cu plus Fe2 plus, and that's the net ionic equation for that reaction. If you have a halogen, now remember that's the group 7 on the periodic table, chlorine, fluorine, iodine. If you have a halogen and a halide salt, you will get a halogen and a halide salt if the halogen is more reactive than the halogen and the halide salt. So for example, you know that fluorine is the most reactive. So fluorine is going to replace any other halide in a salt. So if you have fluorine and sodium chloride, the fluorine is higher on that in reactivity, and so it's going to displace the sodium and end up, displace the chlorine and end up with chlorine gas being produced and sodium fluoride. So that's an example of a halogen being displaced. So moving on to double displacement reactions, and here you see usually these are ionic compounds and things are just going to trade partners. So there has to be some driving force to cause this to occur. Often that driving force is that, say, this stuff is going to form a solid and be pulled out of the solution, and that actually causes the reaction to move forward. Sometimes that driving force might be that we have here an acid and a base, and one of the things they're going to produce will be water, and that will drive that reaction forward. One of the products must either be a water, a gas, or a solid. And a solid, remember, is just another word for saying this stuff doesn't dissolve in water. So often you're going to need to remember to use those solubility rules that you have kind of memorized by this point. And also be sure you watch, because a lot of these, almost all of these, will be some kind of net ionic equation going on. So you may see these written in a lot of different forms, but on question 4 of the AP test, you will have to write it in net ionic equation form, and they usually show you an example of that in their example at the beginning of the test. So that's there as a reminder. I'll just look over it. It must produce either water, a gas, or a precipitate. Something has to drive the reaction forward. So use your solubility table, use solubility rules, use things like that to predict the reaction. Complex ion formation. This is the 6th type of reaction. And this kind of reaction is when we have a Lewis base that forms complex ion. Now these are called ligands. Now some common ligands are the cyanide, ammonia, or things like bromine, iodine, common ligands, chlorine. Now, here we see, remember, the ligand. Here we see the ligand with a metal. Now, these are often transition metals. They often combine with one of these Lewis bases to form a complex ion. So here we see complex ions. Complex ion. Sometimes, usually, it's going to be a metal and one of these bases that form the complex ion. Those complex ions can sometimes have a positive charge, so they're a cation. Other times they'll have a negative charge, so they are an anion. So this complex ion then combines with either a positive or negative counter ion to form a compound with a neutral charge. These are called coordination compounds. A coordination compounds is the complex ion that we were just looking at and a counter ion. It's an ionic compound. It's electrically neutral, but this thing called the complex ion, and here we have one of them right here, complex ion. So when you see those, you need to recognize these as complex ions. They may either have a positive charge or a negative charge. Here you see copper with either a coordination number of 2 or 4. Now that's copper with a charge of +1. If you see copper with a charge of +2, its coordination number is 2 or 6. So it says often the coordination number is twice that of the charge. writing the reactions that form the coordination ion requires, first of all, that you recognize the possibility that we're going to form this complex ion. And the knowledge of the metal ions likely to form coordination ions, and of what the common ligands are, things like this or this. It may be useful to keep in mind that the number of ligands attached to the central metal ion is sometimes twice the oxidation number of the central metal. So here, because this silver has a charge of +1, we see that we have 2 ligands attached here. Or this zinc, you see, is +2, so we have 4 of the hydroxides. Writing the reactions that form the coordination ions required. The breakup of these coordination ions is frequently achieved by adding an acid. The products of the metal ion and the species formed when the hydrogen ions from the acid react with the ligand. There are some organic reactions that you need to kind of be familiar with, and I would suggest going to the organic reactions section of the web page, because they probably provide a better overview than we're going to take time to do here. Thank you for listening.